So I'll start with the history of physics and electronics. So the history of physics, actually it all started with studying light. And so I'll start with some code. This is a Sanskrit code. So this is a general code, and also the meaning is we should all go for the truth. And this is a scientific kind of carries a scientific thought also. We should all go, try to search for the truth, the real, and also the knowledge of imponderability. So okay, so the so this study of actual physical phenomena actually all started with light, and also study of objects, which is kinematics and study of light. So I'll here briefly talk about the study of light and electricity and magnetism, because that is what led to the modern science, basically. So in the ancient era, everyone was aware of the properties of the light rays, like straight line moves in the light moves in a straight line and gets reflected from a surface, and also can get refracted through a denser medium. So if the light goes from a lighter medium to denser medium, it will get refracted. And some notable scientists and mathematicians who have studied this include Pythagoras, Democritus. And why? Because at that time they are developing the geometry, which is called the Euclidean geometry now, and they were studying various geometrical relationships. And then when they postulated that light moves in a straight line and gets reflected and gets refracted, and they started to study how the reflection will take place, how the reflection will take place, and so on. And also they are asking many questions on how do we see colors, how do we actually see an object, and things like that. So there was kind of philosophy that was going on at that time in Greek and other parts. Uh, so the mathematicians and that time physicists and scientists who studied light rays include Pythagoras, Democritus, and Democritus is actually, you probably all know that Democritus first postulated that there must be some invisible element called atoms, and the father of atom, Democritus, and Empedocles reasoned or postulated that the speed of light is not instantaneous, and there must be a finite speed of light. And then Aristotle has his own philosophy of how we see, whether the light goes from our eyes to the object, or the light comes from the object to our eyes. And there was this Euclidean and Euclid's disciples, their version, and Aristotle version, and things like that. And Archimedes is known for a famous experiment with mirrors, and Archimedes also devised some equipments or armory, basically, uh, to fight wars, and using mirrors, and how you can use mirrors to concentrate rays and things like that. And Seneca, again at that time in Anno Domini, before 4 to 65 Anno Domini, and started describing how we see colors, how we see rainbows. So at that time, this theory was there. And then hero of Alexandria, Ptolemy, Alhazen, they were studying different kinds of mirrors, because at that time geometry was getting developed, Euclidean geometry, and they are studying different kinds of mirrors, like circular mirror, cylindrical mirror, parabolic mirror, elliptic mirror, and so on. Because at that time there was studying of this all kinds of conic section, and what will happen, how the reflection will take place, because the laws of reflection was known for a long time, that the angle of incidence is equal to angle of reflection, and using this law they were studying all these things. And then Theodorik Friedberg from started studying refraction, uh, and Galileo Galilei invented not invented, but developed a telescope. And Kepler started to look at the sky, Galileo Kepler, and again contributed to the development of the telescope. And then Willie Snell discovered or written down the laws of the refraction, which is known as the Snell's law. And then Rene Descartes developed the Cartesian geometry, how you can write down mathematical equations of geometrical relationships and describe the law of Snell's in terms of sine functions and so on. And Pierre de Fermat postulated that the light takes the least time from moving from one point to another, and thus derive the formula of reflection and diffraction from the principle of least time. Then Isaac Newton started working on colors, prisms, and so on. Romer also tried to measure the speed of light. So there were all these developments going on in the ancient era, only based on ray optics, which is now called the geometric optics or ray optics. And and then Newton started to give a theory why light behaves like rays, and which is known to as Newton's corpuscular theory of light. Then uh, in the next era, which is known as the scientific revolution era, the viewpoint on light changed. And previously, it was thought that if you have an obstacle, then there will be shadow behind the obstacle and no light. But then the viewpoint changed, and uh, at that time, scientists started to see or started to prove that light behaves like a wave, like water waves or sound waves and things like that. And then behavior of water waves, sound waves were all known at that time. And then the work actually started with Francisco Maria Giraldi, but that was not noticed for a long time. And also Robert Hooke used microscope because also microscope was developed at the time, used microscope to see interference pattern, which is today known as Newton's ring. Because Hooke and Newton work at the same time, so this is known as Newton's ring, which is the interference pattern. And then Christian Huygens developed the wave theory of light, and from Huygens' principle, uh, Huygens also proved the laws of reflection and refraction. And during that time, it was thought that light is a longitudinal wave like sound wave. But then Thomas Young did many experiments and postulated that light is a transverse wave. And the famous Thomas Young's double slit experiment, which is shown here, the right side. So this is the interference experiment, and this is the diffraction experiment. So from interference experiment, Young first proved that light is a wave. And then on the diffraction side, Joseph Fraunhofer, Augustin Fresnel, Francois Arago, Poisson, and many others work on that side. And so there are many different diffraction regimes like Fraunhofer diffraction, Fresnel diffraction, and things like that. And Arago also postulated the diffraction and actually did an experiment, I think. And Poisson initially didn't believe that light is a wave, but then changed his mind, and then also worked on the wave theory of light. And then Michael Faraday also worked on the polarization of light. Huygens also worked on the polarization of light, and these things and the polarization of light, because light is a transverse wave and it has two transverse motion direction, can have two polarization. Uh, and Michael Faraday worked on polarization of light, how the polarization of light changes in effect of inner magnetic field, and so on. These are the development in that scientific revolution era, and which proved that light is not a particle, it's a wave. And then the wave nature of light was the prevalent one at the time, and they discarded that particle nature of light. And then very famous experiment to prove that the speed of light is finite, is not instantaneous, is very important, because that led to the postulate of special theory of relativity by Einstein in 1905. So that speed of light is finite. So that was measured before that light has a finite speed by many astronomical observations by Romer and James Bradley, and then some earthly observations by Fizeau and Foucault. And also Albert Michelson developed the interferometer, and using that also measure the speed of light. So during this study, there were many so during this study, there was many instrument that was invented, and we start with invention of telescope by Lippershey, and from Lippershey, Galileo learned how to make a telescope, and Galileo Kepler kept on making different telescope with higher and higher resolution. And then Murray Hall, John Dolan, all are contemporaries, and John Dolan tried to patent the idea, and Gauss, Fraunhofer also worked on the diffract on the wave theory of light and how the wave nature of light will change the uh, nature of the image, and how you can make better and better lenses, things like that, and aberration corrected lenses and so on. So all these things are developed at the time, and then there was development of microscope by Jensen and Lippershey also, and then Anthony van Leeuwenhoek took the idea and is famous for the invention of the microscope, but he already started before that, and then Ernst Abbe and others. So also invention of telescope and microscope are very important, because from this you started to studying other laws of physics, basically. For using telescope, Kepler studied the motions of planet, uh, and from there you got the law of gravitation and things like that. And using microscope, there were studies of Brownian motion, and from Brownian motion, uh, Einstein first. So Brownian motion, Einstein first postulated that Brownian motion is because of random motion of atoms, and at that time there was no experimental proof of atoms, and Brownian motion was then one of the indirect proof of existence of atoms. So that was very important, and then even more important was invention of spectrometer by Fraunhofer using a diffraction grating. This is the image of spectrometer. You have a source and diffraction grating, lights get diffracted, and uh, and then you get different frequencies. You can resolve it in different frequencies, uh, and you take those frequencies, the intensity of the frequencies, and that's called the spectral decomposition of the original light. So that was the invention by Fraunhofer, and then spectroscopy became an experimental science. And at that time, studying of spectral decomposition of different kinds of light from different sources were studied, basically. And Gustav Kirchhoff also contributed to the study of spectroscopy, and that led to the development of quantum mechanics, basically. That I'll talk in a few slides later. And then another important development was development of interferometer. Michelson started, I would build the first interferometer known as the Michelson interferometer. And this is the image of the Michelson interferometer. You just split the beam in two parts, and then detect the constructive or destructive interference at the detector side. And then Ludwig Mack and Ludwig Gender invented, which is known as the Mack-Gender interferometer, and Jacques Fabry and Alfred Perot invented the Fabry-Perot interferometer and things like that. So interferometer is also very important today, because the detection of gravitational wave was done by laser interferometry, uh, which is called LIGO, Laser Interferometry Gravitational Wave Observatory. So LIGO experiment detected the gravitational wave. So interferometer is very important. And at that time also the Michelson-Morley experiment, which rejected the idea of ether, based on this interferometry experiment. And then that was the optics part. Then there was magnetism and electricity part in that era. And so magnetism was known for a long time, and they found a stone which was already magnetized and can attract iron, pieces of irons. Which is known as the magnetized, and this piece of magnetite, if suspended from above, will rotate itself and align with certain particular direction, and that's how the magnetic compasses are invented. And then people knew about the static electricity and found static electricity by rubbing different kind of insulating materials like amber, fur, wool, glass to each other, and they found different kind of electricity and things like that. So these two things were known for a long time, and they have studied also the phenomena of lightning, which is nothing but static electric discharge by natural means. So these are examples of magnetism and static electricity, and it started from a long time ago, and then uh, Cardano and Aman, and they all started working on this static electricity, amber, fur, wool, glass. And then the main contribution to this field was by one of the main contributions by Gilbert, who studied magnetism and found and uh, postulated that this magnetic phenomena, which also attracted some kind of material. So initially, both were kind of attraction, but first they found out that these are different kind of phenomena, which is, and they call one of them magnetism and one of them called electricity. And then word electric came from the word amber. So basically, and then Cabio and Brown, they actually uh, did some experiments and have shown that magnetism and electricity are different phenomena basically. And then Otto von Guericke is famous for invention of different kind of static electric equipments. And then Robert Boyle, Stephen Gray, and Dufay, they have invented that there are two kinds of electricity, and equal opposite charges attract, equal charges repel, and they found all these things basically. And then Peter von Musenbroek and Kleist, they uh, experimentally found the effect of capacitors, which is known as the Leyden jar experiment or Kleist jar experiment. So they found condenser. They called it a condenser. It can condense electricity, which is nothing but the capacitors. And then Benjamin Franklin did some experiment, uh, and the famous experiment that probably many of you know is he flew kites in a rainy day with when there was lightning happening, and the main purpose of the experiment was to show that electricity can flow. It's not only just static electricity, so used a metal wire and things like that that can flow electricity. So the electricity can flow to the metal wires. So that was uh, beyond the static electricity experiment. And then Watson also and Franklin also proposed that the electric charge should be conserved. Watson proposed the same thing. And then came experiments on how what is the force, what is the magnitude of the force of attraction or repulsion. And Mitchell shown the inverse square law for two magnetic poles, north poles and south poles of two magnetic bars. Cavendish did some experiment, and then Priestley and Coulomb found the inverse square law for electricity, for static electricity, and Coulomb did an experiment. He invented it. He used a torsion balance to do an experiment and to show that indeed the inverse square law formula is valid. And then Luigi Galvani and Volta started experiment on different kinds of electricity, electricity from chemical reactions, electricity from animals, and things like that. Volta is famous for the voltaic cell, and Humphrey Davy and others. were doing the experiment. And the main experiment of all the were scattered. Like they were studying static electricity, magnetism, uh, moving electricity, things like that, different. And then the next, the big breakthrough came, and which is unification of optics, magnetism, and electricity. And that was started uh, mainly from Ampere and Biosavart, Oersted, Ampere, and Biosavart. So at that time, Gauss developed the uh, Gauss law, Gauss divergence theorem, which converted the Coulomb's law to the Gauss law. And then Poisson, you all know about the Poisson, you all know about the Poisson equation. So they were mathematicians basically. They contributed their mathematical formula equations to the physical theory. So they formulated the physical theory in terms of the mathematics, and then Hans Christian Oersted performed experiment and have shown that current carrying wires can create magnetic fields and will deflect the compass nearby. And then Ampere also showed that two current carrying wire can attract or repel each other. So that was showing that magnetism is related to moving electricity. And then Biot-Savart also contributed to that field and formulated some mathematical equations, like some mathematical relations and things like that. And then Ohm's gave the famous Ohm's law, which is the electricity in the electric current in a wire is proportional to the applied voltage, and proportionality constant is conductivity, or voltage is equal to I times R, current times the resistivity, which is known as the Ohm's law. And then Michael Faraday did experiment with magnetism, and so I have shown that change in magnetic field or magnetic flux or can also create current, which is known as Faraday's law. And then Fechner postulated a relationship between Ampere's law and Faraday law. Lange and Neumann, Weber all contributed towards this Faraday law, Ampere's law, and other things. So they were developing the theory. They were trying to find different kind of uh, mathematical formulations at that time, how two wires will attract, what will be the force between them, if you make a solenoid, how will it behave, and things like that. And then many mathematicians like Riemann, using the theory of Lagrange, and Lord Kelvin using the theory of Fourier, analyze all this kind of electricity. And initially, electricity was thought like a flow of something, some kind of fluid. It was not thought of flow of particular electron particles. So their fluid theory of electricity. And then Kirchhoff again contributed to and developed it, and actually developed the theory of transmission of electricity at finite speed, electromagnetism phenomena. And before Maxwell, almost derived that speed of light with a square root of two-factor mismatch, basically. And then James Clerk Maxwell combined all of their studies and just made a small modification to the Ampere law, which is now known as the Ampere-Maxwell law, and then formulated the famous Maxwell's equation. So I have here I have shown all the Maxwell's equation. So these are, the first one is known as the Gauss law for electricity. This is the Gauss law for magnetism, and del dot B equal to 0. 0 means there is no magnetic monopole. D is the displacement vector, E is the electric field vector, epsilon is the permittivity. And on the right hand side, as I have shown that the first law is the Faraday law, which is change of magnetic field can produce a electric field or electromotive force. And then without this displacement term, this is known as the without this term, this is known as the Ampere's law, which is the current carrying wire can create a magnetic field, or current will create a magnetic field. But then Maxwell added that term, which is known as the displacement current, which is change of electric field, can also create a magnetic. And this P is related to H by this permeability. epsilon is permittivity, mu is called permeability. And using these equations without the source term, Maxwell have shown that the electric and magnetic field will propagate in free space with the speed of light. And the speed of light was calculated because the permittivity and permeability of free space was known, and then the speed of light was calculated. Time c is 1 by mu naught epsilon naught. So that was Maxwell development, and then Lorentz gives the Lorentz force law, which is also very important because how an electron, then at that time the study of electrons as a particle started, and the how an electron will feel the force was given by Lorentz force law. And many other scientists like Helmholtz, Poynting studied on the energy of the electromagnetic field and formulated that Poynting vector. Helmholtz, Harsh, Oliver Heaviside, they are all engineers also. Like Harsh was demonstrated the propagation of electromagnetic field, creation of electromagnetic field from dipole, which is known as the Harsh dipole. Oliver Heaviside also formulated a concise vector notation for the Maxwell's equations. So initially, Maxwell's equations were many long equations written in component-wise form. So a Heaviside just uh, made use of the vector notation so that we can write down the Maxwell's equations in this compact form, and also contributed to the study of propagation of electromagnetic field, transmission line theory, and things like that. And Lord Rayleigh studied the scattering of electromagnetic field and explained the blue nature of blue, why the sky is blue, the blue color of the sky. And then Fitzgerald and Boyd have tried to show that this actually violates classical Galilean relativity, and that's how the special relativity was born. And Albert Einstein gave the theory of special relativity, and special relativity is actually comes from this Maxwell's equation, basically the invariance of this Maxwell equation in coordinate transformation. That started with Lorentz, Fitzgerald, known as Lorentz-Fitzgerald transformation, also Boyd, Ulmer Boyd. And then Einstein, actually the contribution of Einstein was the postulate of the speed of light and view of time and space in a unified way, like space-time. So then other scientists and mathematicians contributed. So that was all in that period, which is optics, magnetism, and electricity, all unified. And then there was the birth of this engineering and invention of electric and electronic devices. So first telegraph was invented by Morse. Telephone was invented by Alexander Graham Bell, and the most important contribution came from wireless transmission, which is called radio communication, and wireless telegraph. Started with Jagadish Chandra Bose and Marconi, Braun, Fessenden, and others. So that was how that was very important at that time, the wireless communication. And then electric generator, motor, transformer, all these machines were built up. Then you can create electricity, you can transmit electricity using transmission lines and things like that. And that started with many other scientists like Jet Li, Ferraris, Nikola Tesla. And Nikola Tesla has over 700 patents, very famous. Thomas Alva Edison, Blatty, Parsons, Siemens. And Siemens, you probably know the unit of conductivity in SI is Siemens. So that's by name of Warner Siemens. George Westinghouse and others. That was not only study of physical phenomena, that was how you can use the knowledge that you have gained to engineering applications. That is a revolutionary era And then another revolution started with the invention of vacuum tubes. Now, at that time, Plucker and Hitchcock first invented the cathode ray, and then uh, gas discharge tube was invented, which is by Goldstein and Crookes, and that was known as the Crookes tube. And J.J. Thomson first proved that the cathode rays are electrons and determined the charge by mass ratio of the electron by Joseph John Thomson, J.J. Thomson, and thus proved that electron behaves like a particle and things like that. And then also Philip Edward Anton Hall Leonard also worked on theory of cathode rays and cathode ray tubes. So that was they got the Nobel Prize also. So that many of them got the Nobel Prize, but the Nobel Prize started from 1900. So before that, yeah, of course there was such prize. So yeah, so they worked on the cathode ray tubes, and then Braun and Thomas Alva Edison worked on the light bulbs. And while working on light bulb, cathode ray, and cathode ray tube, they are trying to reduce the vacuum inside that tube. And that's how they invented the vacuum tubes. Was invented by Swan and Fleming. Then Fleming invented what is known as the cathode ray tubes. So vacuum tubes, cathode ray tubes operating different principles. So initially there was this discharge of gas inside the tube, but slowly they started this emission of electrons by thermionic emissions, which is known as hot cathode emission. And then they tried to control the current in the cathode ray tubes, and they invented a device which is known as triode, and the triode was invented by Lee De Forest. And after the invention of triode, you can build amplifiers and logic circuits and other things. And that's how the revolution in the computer science, or basically electronic devices, started by the invention of the triode. So that was very important, which is the invention of triode, which came because of all these previous studies on this optics, electricity, and magnetism, and study on electrons. So at till this point of time, everything was classical mechanics, but classical mechanics started to fail. So couldn't explain many things. So that was the end of the classical mechanics and beginning of the quantum mechanics. So it started with failure to explain the black body radiation spectra. So black body radiation spectrum is you measure the radiation. So you have this, you can measure the intensity and you can measure the energy, but each frequency interval, and then you plot that curve, which is the spectral energy with frequency that was plotted. And at that time, there was classical mechanics and classical thermodynamics and Boltzmann distribution, also known as Maxwell-Boltzmann distribution. And that was actually used to explain the nature of the black body radiation. And because the nature of the black body radiation was known, it was an electromagnetic wave, and how these electromagnetic waves are created because of motion of atoms. And they knew that dipole creates electromagnetic radiation. So they already knew that heating creates a motion of atoms, and that creates the electromagnetic radiation. And they tried to use that theory of classical mechanics to explain the nature of black body radiation. So black body radiation, actually, the classical mechanics do not explain. Why? So this card here, the classical law, which is known as the Rayleigh-Jeans law. This Rayleigh-Jeans law is here. This dotted one. So you can see it cannot explain the phenomena for higher and higher frequency, which is known as the ultraviolet catastrophe. So then Wilhelm Wien gave a kind of uh, fitting formula, empirical formula, based on some kind of hand weaving arguments, and try to fit the data. And this is the Wien's formula, which is this pink curve, which is the dotted curve. But that couldn't, that was able to fit the data for higher frequency range, but for lower frequency range, where the classical law, at least the classical law here, classical law was valid, it was unable to reproduce the classical behavior. And then Max Planck came with the idea of quantization of energy and gives the Planck's law, which could explain the black body radiation spectrum. So there is a typo, black body radiation. And Wilhelm Wien worked on black body and gave the Wien's displacement law, which is the maximum of this radiation spectrum, and is dependent on temperature and the product of the wavelength lambda times T max, lambda max, where lambda is maximum times T is constant. That's why this one, the maximum shifts. So the value of the lambda with the temperature noted here, lambda times T is constant. That was the Wien's displacement law. Wien also got the Nobel. And then there was this study of photoelectric effect. It started with Hertz. Hertz first discovered the photoelectric effect by doing an experiment. If you shine light, there will be electrons emitted from certain materials. They call it photoelectrons because of application of light. And then Lehner also worked on photoelectric effect, but they was, I mean, Hertz and Lehner were unable to explain photoelectric effect from classical phenomena or classical physics. And then Albert Einstein took the idea of Max Planck of quantization of energy, and then Einstein proposed. So Planck's idea was quantization of energy only. Energies are quantized, and then Einstein took the idea and proposed quanta of light itself, which is termed as photons. So these are quanta of light itself, and these are like particles. And the reason behind postulating such things was already Einstein had calculated this special theory of relativity. And the special theory of relativity, the energy E square equal to p square c square plus m square c to the power 4 for any particle of mass m and momentum p for any particle. And already it was known that E equal to Pc from electromagnetic wave theory. So Einstein postulated that photons must be particles with mass m equal to 0. So that was another idea behind Einstein, this kind of postulate that at least light itself is quantized in terms of photons, and explain the photoelectric effect. Photoelectric effect is also very important because after this discovery, there was this X-ray photoemission spectroscopic instrument that is based on the photoelectric effect, and also we have solar cells today that's also based on photoelectric effect. And then even at that time, after explaining black body radiation and photoelectric effect using this quantization of energy, that light is actually particle and is not electromagnetic wave, and the wave theory of light is not valid. The classical wave theory of light is not valid. Was not there were debates in the community, but after Compton made the experiment, the scattering of light by other particles, which is known as Compton scattering, the particle nature of light was well established. That was the end of the wave nature of light and the beginning of the particle nature of light. And one that is one part of the beginning of quantum mechanics. The next part of beginning of quantum mechanics is the end of the particle nature of electron and beginning of the wave nature of electron. And how it started. So this is the emission spectra of hydrogen. So as I told you, Fraunhofer actually developed the spectrometer, invented the spectrometer, and started studying spectral decomposition of light from different sources. And Bunsen also contributed to that field. And you probably know Bunsen by Bunsen burner. In chemistry, you probably all have worked on Bunsen burner. And then Kirchhoff, Angstrom, and Stokes. They were working on spectra uh, of different sources of light, uh, and they found that there are particular spectral lines, and there are two kinds of spectra. One is emission spectra, another one is absorption spectra. And so, if you take a white light and pass it with heated gas of molecules and measure the spectra, what you will get the absorption spectra, and then after some time the gas molecules will emit some spectra, and if you measure that you will get the emission spectra, and the white light has all the spectra that you are assuming. Even if you take light from sun, it will not have all the spectrum, because in sun's environment there will be some wavelength which will be absorbed because there are heliums and hydrogens also. So basically, but if you take some, you can take some white light that has all the spectra, then you can basically measure the absorption and the emission spectra, and then they found different spectral line. And they started the relationship of the spectral line, how the spectral lines are shifted. Balmer, Spassen, and many G-Man, they all worked on the spectroscopic experiment, and that's how the model of atoms came. And then we all know about the Bohr, Sommerfeld, and Rutherford Bohr and Sommerfeld model of atom, Rutherford experiment, and Rutherford has shown that atom has a nucleus and most of the parts are empty. And then came the Bohr model, Bohr Sommerfeld model, and then Schrödinger gave the wave equation, and Schrödinger, Dirac, Heisenberg, Pauli, and others gave the birth of the. So yeah, so this Bohr, Sommerfeld, and Rutherford were all quantum mechanics. Schrödinger gave the wave equation, which is known as the wave mechanics. Dirac, Heisenberg gave a matrix formulation of mechanics, and also Jordan and other. Jordan was with Heisenberg and Dirac and Schrödinger also at that time. So gave the matrix mechanics, and they were trying to explain the behavior of this spectra, because already Balmer, Spassen have formulated some uh, empirical formula how the spectral lines will, what the spectral lines will be, and things like that, which is known as the Balmer series, Spassen series, and so on. So that was one part of the story, which is studying atomic spectra and birth of atomic physics. And then de Broglie proposed that since light is a wave and behaves like a particle, then electron must behave like a wave, because electron is particle classically. And that was the de Broglie matter wave hypothesis. And then Davison and Jarmar have shown that indeed electrons get diffracted from crystal, which is known as the Davison-Jarmar experiment, which is very famous. And then Klaus Johnson have shown interference of electrons in a double slit experiment. And this is again the double slit experiment where you send electrons from electron beam gun and send it through two slits and On the screen, you detect where the electron lands, and you will see an interference pattern, just like the interference pattern of light. So electrons actually behaves like that. And then there was the invention of electron microscopy, because once we have wave, there were already, it was known that we can build microscopes. So that was the invention of electron microscopy by Roscoe and all. And then at the same time, there were experiments on X-ray diffraction, X-ray electromagnetic wave, but it gets diffracted from crystal, and you can study the structure of the crystal and study the arrangement of atoms. And then at the time, the atoms were well established after all this experiment and theory. And then Max von Laue and William Henry Bragg and William Lawrence Bragg have shown that diffraction, X-ray diffraction uh, by atoms, and that have opened up a study of crystallography. And then that was used in biology, chemistry, uh, physics, and many other sciences. So that was the brief history of how we got quantum mechanics. But actually, the main nature of quantum mechanics was in the about uh, uh, not just explaining, not just the behavior of some quantum of particle or quantum of energy. It was the nature of uncertainty or probabilistic viewpoint, and that was very clear to Einstein once he proposed the idea of this Einstein idea of Planck, quantum of light or particle viewpoint of light. And why is that? And that if we study the polarization of light, and if we look at the polarization of light from a particle viewpoint, then it will be very clear. Because what is polarization of light? Because light is a transverse wave. It can have two polarizations independently, and you can either call it circular right or left circular polarization, or polarized if this moves in some g direction, then you can call it polarized in the x and y direction. So it can have x and y directional polarization and mixer of that many polarized wave, and that will be an unpolarized wave. But if you pass it through a polarizer, which is known as polarizer, uh, this is nothing but atomic arrangement, particular arrangement of atoms that will filter the one of the polarization and pass only one polarization. Then you get a linearly polarized light, which is only polarized in the one direction. Now there is a law. So if the original intensity is I naught, then and if so okay, so if this is when you have an unpolarized light, if you get a polarization. Now if you have two polarizer, if you get one polarizer like this, and you have another polarizer, which is, I'm drawing it here, another polarizer which makes some angle with this axis theta. So the intensity that will come out of this polarizer is given by the original intensity I naught times cos square alpha. That is known as Malus's law. So you have, if you have two polarizers which are not aligned, then the intensity will reduce, and the total intensity depends on the angle between the two polarizers. So in this figure, if you have, so if you consider first polarizers, second, and this is the third. If you only consider first and second polarizers, so I'm just drawing this. This is the first polarizer, and if you insert another polarizer, the second one, this is the first one, this is the second one. So there will be an angle between them, theta. The intensity of light that will come out of the polarizer will be the original intensity times cos square alpha. And because the amplitude of the light, that's called the electric field amplitude, will be E naught times the cos alpha. And as the intensity square of the amplitude, intensity will be this. And it was known from wave theory. But why it leads to indeterminism and probabilistic viewpoint? Because from Einstein postulate, the energy of a quantum of light, which is a photon, is h nu, and nu is the frequency. So this is the photon energy. Now, after it's passes to the polarizer, the first thing is the frequency does not change. Frequency does not change. Frequency means wavelength. So you can see this is the wavelength or the frequency lambda, that doesn't change. And that was well established in the community, that frequency does not change. Now, if frequency does not change, and if I send one photon, now you can think of doing this experiment by sending one by one photon to the polarizer. So you are trying to send photons on, and now send photons one by one. Now, if there can be classically there can be only two things: either it pass, either it will pass or not, or it won't. So the law can be only either the photon will pass, photon has some property, either it will pass depending on the angle and depending on the polarizer, or it will not pass. And whatever will happen to all the photons, should happen to all the photons. That's the classical law, which is deterministic law. But since the photon energy is equal to h nu, only just by postulating two things, one is photon is a particle, and the second thing is energy is related to the frequency, and that explains the photoelectric effect, then you are in trouble basically. Because how can you reconcile that fact with the fact that the intensity is reduced? You cannot. So it was initially, classically, it was deterministic. Either this will happen or this will happen. But quantum mechanically, any of the two can happen with a probability. Any of the two can happen, and there will be a probability p and 1 minus p of happening. So, and then the probabilistic viewpoint of quantum mechanics comes there. The second thing, which is even strange, is now if you have two polarizer, and let's align this in this direction, and then if you have another polarizer, which is this third polarizer, this is the first polarizer, this is the third polarizer, which is this figure, and this is aligned in this direction, and this third polarizer is aligned at 90-degree direction. So this is aligned in the 90-degree direction. Then no light will pass, because this first polarizer, you can see that these dotted creating lines, and the second polarizer is the third one is the part of first one. This is the third one, which is in the behind, are aligned in the 90-degree direction, and if cos alpha equal to 90 degree, then I will be equal to 0. No light can pass. But once you put a third polarizer, which is some angle, which is at some angle, which is not 90 degree, then you will start getting light. And this is very strange, because putting some obstacle cannot increase the intensity of light at all. Because what you are doing, you are putting some obstacle. And just by putting some obstacle, you are changing the intensity. You are actually increasing the intensity of light. And these two phenomena, one is the probabilistic viewpoint, another one is you are changing the final measurement outcome by doing a measurement before that measurement. So if you have 1 and 3, so you are doing this measurement, light is passing from 3 to 1. Just say that light is passing from 1 to 3. we are shining light on the screen, passing from 1 to 3, and there is some result. Now, if you put another polarizer 2, you are changing the final result, and also you are increasing the intensity. So this is actually the essence of the quantum mechanics, that measurement uh, two measurement can give different results if performed in different order. Also, if you change the order, like if you don't insert the second measurement in between but in the behind, like here, the second one in behind, so the sequence is 1 3 2, not like 1 2 3, then also you will not get any light, because 1 and 3 already filters all the light. So performing the measurement 3 before 2 or measurement 2 before 3 changes the outcome. So these two measurements are not commutative. So this non-commutativity also comes into picture. Non-commutativity. Commutative. So these are all the that's how the modern Schrodinger and also the Heisenberg picture came, and Dirac's operator theory and things like that. So this you will know from experiment on polarization of light. Similar thing will happen with experiment on spin. How? And this is known as the Stern-Gerlach experiment. They were experimenting with silver atoms basically, and silver atom has some field cell, and then one electron in the s orbital. So whatever you will measure the magnetic moment of this atom will be due to spin angular momentum. So they didn't know about the spin at that time. They knew about orbital angular momentum, because that was already there from the time of Bohr and so on. So they knew that. But what is the experiment? The experiment is you create so this is a south pole and north pole, and if I draw the cross section, I have rotated the apparatus, and I'll tell you why. You can rotate the apparatus in any. I have rotated the figure to show you that the apparatus can be rotated basically. Now this is your north pole, this is your south pole, and it will create a magnetic field which is not homogeneous. So you create a magnetic field B in the G direction, let's say, or in these two directions, which depends on the position. This will depends on X and G, and it may also depends on Y, but I am assuming that other direction is uniform. So it will depend on that. And what is the energy? The energy is the magnetic moment mu times the magnetic field B, mu dot B. And you will calculate the force by taking the derivative of this energy. So since there is a gradient of B in the Z direction, now since B has a B has G dependence, and if B is only in the Z direction, let's call it B naught. So and this B is only in the Z direction, B naught, which depends on Z. Then we'll have force will be proportional to some derivative of B with respect to Z, and that will be in the G directional force, because you are taking the Z derivative. So there will be force on the particle, and the particle will move either up or down depending on the direction of the magnetic moment, because the magnetic moment is aligned or anti-aligned. Depending on that, the sign of the force will change. And if you put a screen, then you will get particles concentrating two different area separated by nothing in between, and they call it space quantization at that time, because in space you are getting quantized value. So this is known as the Stern-Gerlach apparatus. And why this is very important? Okay, you may start with some collection of spins, and after one apparatus which is aligned in the z-axis, so let's call this is aligned in the z-axis, you get both the plus and minus, and one is plus oriented spin, another one is minus oriented spin. Now you can, what you can do, you can block all the minus oriented spin and pass the plus oriented spins through another same operators oriented along the same direction. So what you will get, of course you will get all plus, no minus, because you already eliminated this. Now again you do the same thing. You have a Stern-Gerlach apparatus. You start with some source which will have always have some mixture. So you first filter it. So this up to this part we can call it filtering. So we are first filtering everything, and what we are passing to the second apparatus is Z plus. Now second apparatus is oriented in the X direction. So this is oriented in the Z direction. I can orient it in any direction. So I call it Z, X, and Y. So I can rotate the apparatus oriented in any direction. So if I rotate the apparatus, that will be an apparatus oriented around the x-axis. Then what outcome will we get? And it was found the outcome will be 50%, 50%. So 50% will be x plus and 50% will be x minus. Okay. Why? Okay, because Z is kind of 50-50 mixture of x plus and x minus. Because we can see that if I have a z-axis here, and if the spins are oriented along this x-axis, the spins have half of the chance to get quantized in the z, half of the chance to get quantized in the x. Kind of intuitive, you can say. Now, after doing this experiment, we have a 50%, 50%. Now we eliminate all the x minus. Now we started with a Z plus here after filtering. We say, okay, electrons have some property which is Z plus. We know all these electrons have some property, or atoms, whatever we have experimented with, had some property Z plus as well as some property X plus. Now we want to measure the property Z plus again, because here in the first experiment, when we know that if it has some property Z plus and if we measure that property, we'll again get that property Z plus. Now again, we know, okay, some of them has Z plus, some of them have Z minus. Eliminated the Z minus, we have only Z plus, and among them, some of them has property Z plus X plus, some of them has property Z plus X minus. I have eliminated the X minus. So whatever electrons it has the property Z plus and X plus oriented some property. It has some angular, you can show angular momentum in the Z direction and or in the X direction. Now if I measure the angular momentum for the Z direction, which is again orienting the spin-Gerlach apparatus in the Z axis, we'll get again 50% of this. So 50% of the 50% that we started with. So 50% of this and the 50% of the other. So the property that it has the property Z plus is lost already. And because I perform this experiment in between, it changes the result. So if I had performed here, okay, performed along some x-axis, I would have get 50% of x and 50% of x. Here I am getting 50% of z plus and 50% of z minus. So this two experiment, this is Stern-Gerlach apparatus along the x-axis. So z-axis, z-axis, x-axis, and z-axis, x-axis, z-axis. So these experiments are performed in different order. So just by performing different order, we are getting different result, which is the non-commutativity of experimental outcome. And these are all related to the famous Heisenberg uncertainty principle. The reason I wanted to tell you is that these two experiments, this polarization of light and Stern-Gerlach experiment is this. These two experiments actually explain the true nature of the quantum mechanics. Before that, you are explaining some uh, properties, and it's kind of semi-classical in nature. But this is actual quantum mechanics that you know from these two experiments. And then, uh, since have already told you, whenever you have some physics, you are trying to. So why quantum mechanics? Because quantum mechanics actually gave explanation to everything and actually explain the periodic table of Mendel. So explain the periodic table, atoms, molecules, solids, and also solids explain the conductivity of the solids, conductivity or resistivity of the solids. So these are all known before. So explain all these properties of materials, basically properties of all the materials. One failure of classical mechanics I didn't mention here is failure to explanation of magnetism. So this black body radiation actually gives the new Planck's formula, Planck radiation formula, and also changes the statistics of quantum particles, which gives the Bose-Einstein statistics. So these photons follows Bose-Einstein statistics, and the Rayleigh-Jeans formula, which was based on Maxwell-Boltzmann statistics, fails. It fails. The new statistics is known as Bose-Einstein statistics. It was given by Satyendra Bose. And then the explanation of magnetism. So classical mechanics cannot explain magnetism, and in Bohr has derived that, have shown that theoretically in his doctoral thesis and Bohr-Van Leeuwen theorem, and is known as Bohr-Van Leeuwen theorem, that classical mechanics, or at least classical statistical mechanics, cannot explain magnetism. And again, failure of classical statistical mechanics. So this kind of thing, except photoelectric effect and Compton scattering, these two things have shown that why classical statistical mechanics fails. And then we had this old quantum theory, Schrodinger equation, old quantum theory, and then Schrodinger equations, Dirac, Heisenberg, and Pauli, their contribution, and they have the actual quantum theory of atoms, molecules, solids, and so on. And there are many development that we'll study in this course. How crystals, what are the energy levels of a crystal in periodic arrangement and so on. Bloch's theorem, how current flows in crystals and things like that. And then this thought experiment on polarization of light, or this is not thought experiment, the explanation of polarization, this experiment in view of particle nature tells that the indeterminism or probabilistic viewpoint of quantum mechanics inherent in quantum mechanics, so you cannot get rid of it in quantum mechanics. And also the Stern-Gerlach experiment explain this probabilistic viewpoint, that you always have a probabilistic outcome. So and also non-commutativity of experimental outcome and probabilistic outcome. These two things are very important, and that is related to uncertainty principle also, the non-commutativity of experimental outcomes. And then the development of solid state devices started. So first, Lilienfeld patented the idea of a field effect transistor, which is known as APT, in 1925. That was just an idea, and the idea was, so you have a metal. This is a metal layer. This is a oxide layer, or dielectric, basically. Oxide, insulator, dielectric, whatever you can call it. This so, and then by applying voltage between this grade and the body, so you are going to create an electric field through this layer, and then that electric field will attract uh, electrons, and then you can create a layer of electrons here just beneath the interface. And then if you ground it and apply small positive voltage, then the electron will start to flow. So you apply positive voltage here, you ground it, there will be electric field and electron will start to flow. And since the concentration of electron will depend on the electric field here, so you are also applying a voltage here called the gate voltage. Just by controlling the voltage here, or the controlling this field here, this electric field here, you can control the concentration of electron and control the current. That is known as the field effect device, known as the field effect transistor. And transistor, because you have a trans resistance. Trans means applying the third control terminal to gate terminal, you can change the resistance between the source and drain terminal. And that idea was patented by Lilienfeld in 1925. And physicists was trying to make this transistor, fabricate this transistor. But however, they couldn't, because it's very hard to control the interface quality. But in 1947, Bardeen, Breton, and Shockley invented what is known as the bipolar junction transistor, and they got the Nobel Prize for that. And then in 1959, after almost 34 years, first this metal oxide semiconductor, this is a metal, this is a oxide, and this body is a semiconducting material. This metal oxide semiconductor was invented or actually fabricated by Atala and Kong. This was also done in Bell Labs, Bardeen and Breton, and this was also done in Bell Labs, Atala. So they first fabricated this MOS device, and then since bipolar transistor was already there, Kilby and Robert Noyce, Kilby from this Texas Instrument company, and then Robert Noyce was in Fairchild, and then went to started Intel basically. So they invented the monolithic integrated circuits, which is fabricating all kinds of device in only one single semiconductor. So this is monolithic integrated circuits. This is figure from first Kilby's IC, the first IC, and Jack Kilby got Nobel Prize, but yeah, if Robert Noyce were alive at that time, he would also have the Nobel Prize, share of the Nobel Prize. They actually invented this monolithic IC design, and after the invention of monolithic IC design, the number of such devices in a given area has changed, and that gave rise to the famous Moore's law. And yeah. So Moore's law says that the number of transistors which fit into certain area almost doubles in every 2 years. And right now, we have almost kind of 10 billion transistors in a microprocessor. And it started from 1971. And you can see this plot, which is plotted in a logarithmic scale. The powers of tens are plotted. The powers of tens are plotted in equal intervals. So this is a logarithmic plot, and this number of transistors doubles uh, approximately every 2 years. And how this is achieved? This is achieved by scaling the technology. Now the length of the channel, which this is the channel where there will be electrons, which will conduct the electricity, and this length of the channel is called the channel length. And by reducing the dimension of the overall device, you also reduce the channel length. And this is how you reduce this, you do scaling, and this is given the what is the channel length. Starting from 3 micrometer on every year, you are every year you are almost multiplying it by 0.7 times. I mean, actually then reducing it, multiplying it by a number less than 1. So if you multiply with 3, start with 3, you are almost 2.1 or 2, start with 2, you 1.4 or 1.5. So in every 2 years, you are reducing the size by half. And then here we have at this point, and then the question is, first of all, when we are less than some 100 nanometers around this part, we're already away from the classical mechanics, even the semi-classical mechanics. So in this area, all the semi-classical mechanics is valid. But when the size is smaller and smaller and smaller, all the quantum phenomena will start to play. And then will we keep reducing the device? This is the size of atoms. It's already few atoms. Now I'll just show you uh, the comparison. The comparison is so basically molecules which was initially thought to obey, which behaves like classically obeys the Boltzmann statistics or Boltzmann-Maxwell statistics, but photons obey the Bose-Einstein statistics. Phonons, or which is also lattice vibration. Lattice vibration is mode of sounds, but since if photons, electromagnetic wave can be quantized, sound can be also quantized and have some quanta, and that's called phonons, and that obeys Bose-Einstein statistics. Electrons obey Fermi-Dirac statistics, and they are all different from classical. And classically, these are waves. This is a longitudinal wave. This is a transverse wave. But quantum mechanically, it was found out to behave like a particle. Classically, this behaves like a particle. Quantum mechanically, when the size reduces, this behaves like a wave. So there is always this wave particle duality. And if you reduce the length scale, then basically you move to a quantum regime. Like if your mean free path reading gets reduced below 10 micrometer or so. So this was commercial devices in the 1990, which was 1 micrometer that I started showing here, 3 micrometer, 2 micrometer. And then if you reduce below this 100 nanometer, so that was here, this 100 nanometer. So you are already in the quantum regime. So you already have to consider de Broglie wavelength and all kind of things, atomic physics, distance between atoms and things like that. So once you reduce the size, you have to use a different theory. You cannot use the classical theory anymore. And the last, this is the last slide. which to the overall view on different length scale for photon, electron, phonon, different kinds of fluids and things like that. So photon, we had this Maxwell's theory, even the ray, so ray theory and things like ray theory, Maxwell's theory, but they are in different regimes. For electrons, we have this Ohm's law. When the distance is much larger, that is the particle regime. Then we'll have Boltzmann transport equation, and then we have ballistic transport, quantum ballistic transport, and complete quantum mechanics. And complete quantum mechanics always involves superposition and entanglement and things like that, which is meant by this, which is known as the coherence. I didn't talk about superposition entanglement yet, but which is the coherence wave regime or coherence regime. This is the transition regime where you can approximate by some semi-classical quantum kind of equations like quantum Boltzmann equation. Boltzmann equation is semi-classical. You have some quantum correction, you have quantum Boltzmann equations and things like that. Also, you can model by some kind of ballistic transport that can be quantum ballistic or semi-classical ballistic. Similarly, yeah. So this is for electrons. For photons behaves like how the phonon. For phonon behaves like how the photons behave. So for photons, you have Maxwell's theory, because you have very small device like X-ray, high frequency, small wavelength. You have small device. You are probing atoms and things like that. You have to go to the full Maxwell's electromagnetic theory. You can have ray tracing when the device dimensions are much larger, when you are using some kind of lens, and this is in millimeter kind of thing. And if you are using some wave which is in meter range, then wavelength, then you are much larger than this. So you can go to the order of the device. So you can go to the ray tracing and different kind of approaches. So here we will study mainly the electronic properties of matter. We're not going to study photon, and that is the area of optics and photonics. And we'll study a little bit of phonons. And we're not going to study fluid. And this is kind of area of fluid mechanics. Okay, so that's it. I have taken many figures from Wikipedia, Wikichip, many data from our world in data, and these tables from these two books. That's it. Do you have any question? I'll go to the questions, and or you can ask the question in the next session if you want, because we are running out of time now. So some of you have asked to share the attendance link, but attendance link is like I have to give it myself. I cannot share the link with you, so it's in my own portal.
Hello, Dr. Rick.
Hi, Dr. Sanjeev.
How are you?
Yeah, I'm good. How are you?
So thanks for a nice lecture.
Yeah, thank you.
Just one question that the last 4 pages you have shown us from some book, na?
Yeah. So this is 2 books. The slides are taken from these 2 books. One book is by Gang Chen on nanoscale energy transport and conversion, and the one book by Supriya Datta, electronic transport in mesoscopic system.
Right. Thank you, Doctor.
Thanks. Okay. Anybody have any questions? Okay.